Welcome back to module 9 of the course time dependent quantum chemistry. We have presented time correlation function and we have seen that the Fourier transform of the time correlation function is actually giving the spectrum of the system. In order to get that spectrum, I do not need to solve TISE, just solving TDSE I can get that. So, it is a very interesting perspective we have developed for the time dependent Schrodinger equation. What we are seeing is that there is a close correspondence between the time and frequency domain representation. So, we will look at this. In the time domain, what is important to know is the correlation function. So, this is a typical example of wave packet correlation function. Do not expect that this is the way always correlation function will work. This is just one example of correlation function. So, this is called wave packet correlation function, and corresponding spectrum. By doing the Fourier transform. So, we have to do this Fourier transform of this correlation function, we get that. So, question is how the correlation function varies with respect to time. Can we have some idea, generic idea how it is varying, and the entire discussion is developed based on the first proposal given by Heller in 1981, and we are following that approach very closely. So, if we look at the typical behavior of a correlation function, we see that the correlation function is actually always decays, and it should always decay. Because why it should decay? Because I start with an initial function and I am trying to correlate with a function at later time. So, it is quite obvious that at later time this function will be moving away from the initial function, and if it is moving away, then effective overlap will go down slowly. So, correlation function, time domain correlation function will always decay, but the nature of the decay has characteristic time scales. There are 3 different kind of decays will be going on in the it can be 1, it can be 2, but this particular examples we are giving is 3 different times. So, maximum 3 different possibilities I can see in the correlation function decay, but in some situation I can have only 1 decay. So, we need to define what kind of decays we are talking about. Okay. And depending on the situation, I can have 2 different decays, I can have 3 different decays, I can have 1 decay. So, let us look at what kind of decays we have, but it is quite clear that in the end correlation function has to decay, because more time I spend. So, if I start with, let us say so this is, if this is your the first initial wave packet, and if the final wave packet is moving away slowly, then obviously the overlap between the initial and final is going down, and extent of overlap is representing the CT is representing the extent of overlap. So, that is the correlation function. So, it is quite obvious that it should decay, but nature of the decay will depends on what kind of potential the particle is experiencing and many other factors. This is just an example we have shown. In this example, we are showing that 3 different decays are possible. So, what we are going to look for here, the first thing we'll take a look at it is that at t equals 0, my correlation function is nothing but psi 0, psi 0. I have removed the x dependency here for notation only, notational clarity, but it depends on x basically, because this integration is over the x, we have to remember. I have just removed this x from this bracket to make it simple. So, if we look at this correlation function at t equals 0, so this is your t equals 0 time, we see that this is going to be 1 because this is normalized. we start with normalized wave function, we start with initial normalized wave function. That is the first criteria we have set to solve time dependent Schrodinger equation. So, because it is normalized, the first the initial value of the correlation function magnitude would be always 1. There is no exception for that, and which means that from 1 value unity it will just decay. Now, different ways it can decay. One examples we have set, just 3 examples we have shown. So, what are the possible decays we can have? That is exactly what we are going to take a look at it closely. Initial decay of CT may correspond to the time scale T1. So, I can have a time scale T1, and what is this time scale? We will mention that. This decay, so this is one decay associated with this T1 time scale. Now, this decay occurs, this decay may occur as the wave packet moves away from its initial location. So, because this psi 0 psi t, again I have removed this x dependency here for clarity, that is all, but it is the integration over the space. The psi 0 psi t, it is the it representing the extent of overlap, extent of overlap. So, it is the extent of overlap between the initial and the final wave packets, and as a result as the wave packet moves away from its initial location in position space, it is actually moving away. So, my initial position wave packet was this, and then at a later time it is like this, it is like this, it is moving away. Because it is moving away, the overlap between the initial wave packet and the final wave packet is, we are losing that overlap, and that is why it should decay. So, this decay is quite inherent decay of the time correlation function. It should decay because so in I can have a situation where I have only this part for a given system, where correlation function just decays. There is no other reoccurrence like the examples we have given here. This is just a generic view. So, I can have no reoccurrence. So, the wave packet is actually moving away from this initial position to, let us say, plus infinity. It is moving away. If it is moving away, then there is no reoccurrence, and we will have only characteristic time scale of this decay time of this decay, inherent decay. This decay occurs because the wave packet moves away from its initial location. So, this is one type of decay we can have. Another situation we may have where after one period of motion, and that is happening particularly in this kind of harmonic potential, where I have a wave packet here, it can go and it can come here, and again it can come back, and if it is coming back, my starting point was here. So, it is actually again having higher overlap. So, this is the reoccurrence I can have, and if I have reoccurrence, then this is another situation. It is not that for all wave packet will have a reoccurrence. Let us say I have a free particle moving from 0 x equals 0 position to plus infinity. It is actually moving away from the wave packet. So, it will just decay. There is no reoccurrence, but if it is in the harmonic potential kind of thing, then it can reoccur. So, this situation, I can have another situation which will be defined by the characteristic time scale T2. After one period of motion, the wave packet may return to its initial location in position space. And if that happens, then what will happen? I will have a reoccurrence of CT, just like here, what you are seeing here. It is reappearing for 3 times, and this reoccurrence time is defined by this T2. So, this is the time of the reoccurrence time which is characterized by T2 time. We can have another situation when there is a reoccurrence of the wave packet, then I may have another situation. The situation is following. This reoccurrence time, when it is reoccurring, reoccurrence time in CT may also decay with third time scale. These are the all possibilities. It is not necessary that a quantum system has to follow always this. There is a third time scale I can have T3, where reoccurrence is decaying. As you can see, this amplitude, the first amplitude was 1, then reoccurrence, first reoccurrence amplitude is less, second reoccurrence amplitude has become less, and third reoccurrence amplitude has less amplitude. So, it is slowly decaying, this reoccurrence time is decaying, and if it is decaying, then this particular decay is defined by this dotted line, and this decay will have a characteristic time scale, and this characteristic time scale I can call it as T3. One can define that characteristic time scale as a full width half max at the time when the decay has gone to the amplitude of half of the maximum, or it can be defined by some other characteristic time scale, but that we will have a time scale, characteristics time scale, that is T3, and this is because of the reoccurrence decay of the reoccurrence. T2 was just time of reoccurrence, time scale of occurrence. So, how quickly it is reoccurring, that time scale is T2, and how quickly this reoccurrence is decaying, that is defined by T3. So, this kind of decay can is possible in an harmonic kind of, not harmonic, anharmonic oscillator, where things can decay slowly due to dissociation, let us say. So, I am here, so I can have a situation like this, which is going this way, but and then part of the wave function is going away, and the second part of the wave function is coming back, and that is why we can have a less overlap, and we can have a decay in the time correlation function. So, this is also possible. So, these are the 3 possibilities we have, the possibilities for the decay time scale of the time correlation functions we have shown. We will take a look at now what are the possibilities I can have for the frequency domain. So, those time scale which we have defined in the time domain, how does it look like in the frequency domain? And we will see that always there is a close correspondence between time and frequency domain. The first domain, if we recall that the first decay of CT we have characterized as the time scale T1, which is the decay as the wave packet moves away from the initial position. So, that is the way in the time domain we have understood that decay time. Here we will have that time will correspond to some frequency, and that frequency is going to be represented by 2 pi by T1. That frequency is given by this decay in the spectrum, and this part is going to represent that T1 decay time. Now, T1 decay time has to be represented in the time domain. In the frequency domain, we will call it this T1. T1 appears as width, and remember width is also features a decay. So, when we think about a width, this width is actually featuring how things are decaying. So, width and decay they are synonymous in this problem. So, we will call it width or decay, featuring a decay. But mostly decay we consider in the time domain, and in the frequency domain it is decay because it is decaying, but we call it in terms of width. So, T1 appears as width of the spectral envelope. So, what we get is that 2 pi by T1, this is representing the width of the spectral envelope. So, T1 is appearing as the width of the spectral envelope in the frequency domain. What about T2? What we have defined T2? This T2 reoccurrence time, we have reoccurrence time as T2. Reoccurrence time of T2 in time domain. So, that T2 will correspond to the spacing. So, in the frequency domain it is going to be 2 pi by T2, and 2 pi by T2 is going to correspond to the spacing which is nothing but spacing, but when you say spacing between two spectral lines, the spacing between two spectral lines, when you say spacing, it is actually representing the reoccurrence of the spectral features here. So, there is a direct correspondence between these two, reoccurrence of the spectral features. So, it is going to control this 2 pi by T2 is going to control the spacing between adjacent spectral features. So, this is what we have shown. This part is going to represent, this arrow is going to represent, this spacing is going to represent 2 pi by T2. So, it is showing the reoccurrence of the spectral features. But reoccurrence, this terminology we use in the time domain. In the frequency domain we call it the spacing, the spectral, how the spectrum are spectral features are separated in the frequency domain. The third time scale we talked about T3, which is the decay in the time domain. It was associated with decay of the reoccurrence feature. Of CT. That was the meaning in time domain. In the frequency domain, what it does mean? It means that this T3 appears as the width, again width is decay in the time domain of each spectral feature in the frequency domain. So, this part I have to magnify. So, I'll magnify this part first. I will magnify this entire spectrum, spectral features. I'll magnify it. It will be like this, and this T3 is indicating what is the width of each spectral feature. This is 2 pi by T3. So, in the frequency domain, this what you call T3 in time domain, it is going to be frequency in the frequency domain is going to be 2 pi by T3, and 2 pi by T3 is going to be again the width of each spectral feature. In the frequency domain. Now, it is not necessary that width will be same for each spectral feature. In that case, you will have more number of time scale, and each time scale in the time domain is now going to correspond to the 2 pi by that time in the frequency domain, and that is the way we get the close correspondence between the time domain and frequency domain representation. Time domain representation of the correlation function and frequency domain representation of that correlation function, which is nothing but the spectrum. So, what we have realized that if I know the correlation function CT, I will be able to get to know its eigenstate energies. So, I will be able to explore the eigenstate energies of a system. All I need to do is that I have to play with the propagation of the wave function. I can start with a particular wave function, and then I have to propagate it for a long time or convenient time, so that I can include the eigenstate energies of interest. But then question is, once we get these eigenstates, I would like to know, because TISC will give me, if I solve TISC, it will give me eigenstates and eigenfunction. So, En, psi n both will be getting back from TISC. Now, so far with the help of TDSC, I have been able to get this eigenstate energies. Question is, what is the function we get, eigenstate function, and for that we have to go over another, we have to explore another realization, that the Fourier transform of the wave packet at that eigenstate. So, if I am interested to find out the eigenstate wave function associated with the eigenvalue En, I want to find out psi n, then all I need to do is that Fourier transform of the wave packet is psi xt, that is the wave packet I have to Fourier transform that wave packet at that energy, En energy, to get that eigenstate. That is the basic idea. So, I will first prove this idea, whether this is mathematically justified or not. So, so bottom line, what we are trying to make here is that one may obtain eigenstate wave function corresponding to each eigenstate energies using the fact that an eigenstate is nothing but a superposition of wave packet. This is an interesting statement. So far we have seen that wave packet is created by taking superposition of stationary states. Similarly, there is another theory which can be proved that if we take the linear combination of the wave packet, I get back the eigenstate. So both are possible. So wave packet to eigenstate conversion is possible by taking linear combination of the wave packet, and I can again wave packet can be constructed by taking linear combination of the eigenstates. Both are possible. One possibility we have already seen, combining eigenstates. We have created wave packet in many occasions, and but the reverse we haven't seen, and we'll check this reverse is true for getting the eigenstate. We have already seen that time evolution operator can give me psi x. Time evolution operator, this is represented by this exponential operator, this part can give me the wave function at time t if I know the initial wave function psi x 0. So we will make use of this time evolution operator, and we'll try to find out what we try to mean here. So for that we have to consider this integration. What is the meaning of this integration? We'll get to know later, not now. We'll just move forward with this integration. This is very interesting integration. This integration is in mathematical language, this integration is nothing but getting a Fourier transform of this wave packet at time t at the energy En. We have considered En energy. So En, or in other words En by h cut is omega n. So at the frequency, angular frequency omega n, I am taking the Fourier transform. So that's the meaning of this integration. But instead of finding out the meaning of this integration, we can just move forward with this integration, and we try to understand the meaning of this integration. And this psi x will be represented in terms of the time evolution operator. So we will do that. We will insert that expression psi xt into this integration, and we will see that it is we have to insert it, and we insert minus infinity to plus infinity. This psi xt is going to be nothing but e to the power minus I h t by h cut, then psi x 0, then e to the power I E n t by h cut dt. That's the integration we have. Now this psi x 0, we have already seen that this can be expanded in terms of the eigenfunctions like this. It does not have the time dependent phase factor because t equals 0. So this expansion we have already done. So we will insert this expansion here. If we insert it, then what I get is e to the power minus I h t by h cut, then summation of Cm0 psi mx, then e to the power I ent by h cut dt. Or this is not time dependent, so I'll be able to take it out, and if I take it out, then what I get is Cm0, then minus infinity to plus infinity e to the power minus I time evolution operator acting on this eigenstate wave function e to the power I ent by h cut dt. So, this is the integration, finally integration we get. So, what we see that I have an operator, time evolution operator, which is acting on the stationary state, and when time I'll prove that one, but when time evolution operator acts on its eigenstate, what I finally get, it is actually nothing but emt by h cut psi mx. This we will prove very soon. We will prove it in the next slide. So this integration, this is what we started with, is nothing but now this integration, as we have taken the time evolution operator, and now we will be able to prove that this e to the power minus I ht by h cut psi mx is nothing but e to the power. So, this time evolution operator can be very easily find out what is the value, and in order to find out the value, we will use the Taylor series expansion that we have always done for the time evolution operator, because in an exponential operator we take the Taylor series expansion and we get minus I ht by h cut, then plus 1 by 2 minus I ht by h cut whole square, plus like this way, and this is going to be psi mx. And if we see that if this operator is acting on this psi m, we know that h acting on psi m is going to be em psi m. That's the time independent Schrodinger equation. Similarly, h square acting on psi m is nothing but product is going to be operating it twice, which is nothing but first it will operate and it will give me psi m, then it will give me this. So, what I get here, this is nothing but 1 plus minus I emt by h cut plus half minus I emt by h cut whole square, like this, psi mx. This is nothing but the exponential function of emt by h cut psi mx. So, what we have done, we have proved that this part can be written in terms of the in terms of the this simplified form, and as a result we get this form where we do not have time evolution operator, we have now time dependent phase factors, these two time dependent phase factors, because we are going to insert this one here and we get the time dependent phase factor. Once we get this time dependent phase factor, we know that em by h cut is nothing but omega m, and en by h cut is nothing but omega n. So, we can insert that, and what we get here is that this part is nothing but m Cm0, then minus infinity to plus infinity e to the power minus I omega mt, then psi mx, then e to the power I omega nt, then dt. That is the integration we have. And is if we look at this integration, this is quite similar to writing like this, summation of Cm0, then we will clearly write down summation of Cm0, then this is psi mx, then this integration is going to be minus infinity to plus infinity e to the power I omega nt e to the power minus I omega mt dt, and we have seen that this form gives me the delta function. So, this integration, entire integration can be written as Cm0 psi mx then delta mn, but this is not just delta mn, we have 2 pi factor then delta mn. This is the form of the delta functions we are going to we have used. So, delta, so we have to write down not delta mn, it is actually delta omega n minus omega m. So, if we now this summation, if we do this summation, continue this summation, then only function which will exist is this part Cn0 psi n x, because it is for m equals n, which is omega n equals omega n, this delta omega n minus omega m will be 1, all other terms is going to be 0. So, that is why the summation will end up with this simplified form. And what is this simplified form? We are seeing that we are actually calculating this integration. So, what we are getting, this integration minus infinity to plus infinity psi x t e to the power I e n t by h cut dt. This is actually proportional to psi n x. What is psi n x? Psi n x is the eigenstate. This is the eigenstate wave function psi n, and I am doing this Fourier transform at En. So, corresponding to an eigenvalue, I am now getting an eigenstate wave function, and that is exactly what we wanted to do, because TDSE is giving me this two informations together. Similarly, TISE has given me these two informations together. Now, I am looking at through TDSE, and through TDSE we are now seeing that the Fourier transform of the wave packet at the energy. So, the basic idea is that the meaning of this integration is that the Fourier transform of the moving wave packet which is psi x t moving wave packet at the eigenvalue En is actually giving me renders eigen state wave function. So, if I Fourier transform the entire wave packet at that energy En, then I get back corresponding eigenstate wave function which is psi n. And psi n, here psi n is the eigenstate wave function of the Hamiltonian corresponding to the eigenstate energy En. So, we have come to the end of this module. In this module, we have gone over a very interesting perspective of the TDSE. Generally, we think that TISE I need, time independent Schrodinger equation I need to find out the spectrum of a system, which is energy level of the system and corresponding eigenstates and wave functions. But what we see here from this exercise in this module, that TDSE solution to TDSE can give me an wave packet at time t, and I can correlate that wave packet with the initial wave packet to get the correlation function, time correlation function, and Fourier transform of the time correlation function gives the spectrum of the system, and spectrum has all this information, energy level information. En information is taken from the spectrum, can be taken from spectrum. On the other hand, the same wave packet at t equals time t, later time t, if I Fourier transform that wave packet at that particular energy, then I get back the wave function corresponding to that eigenstate. We will stop here, and we will meet again for the next module.